So what we're going to look at here is an actual application of the capacitors in an RC op-amp circuit. If you'll recall, we had RC op-amps that had a characteristic feedback resistor, and we'll see how the capacitor behaves when it takes over that role, at least in one of these two solutions. So we see that we have a differentiator and an integrator. In the differentiator, the capacitor replaces a resistor as we studied it before in an op-amp circuit on the input side. And then in the integrator, the capacitor actually takes over the role of the feedback resistor. Now we're going to do a little bit deeper dive into understanding how the differentiator and integrator circuits work. We're going to return to using KCL on an op-amp analysis, circuit analysis, just as we did in our earlier chapters. We're going to be looking at node V- and considering what the currents are that come in or go out of that particular node. If we use our standard KCL techniques, we'll see that the derivative of the, with respect to time, of the input voltage V1 minus V minus times the capacitor value plus the difference between the output voltage V naught, which is our desired voltage, minus V minus, is equal to the current that goes into the minus input signal port on the op-amp. We now take into consideration two of the key ideal op-amp rules, that V minus is equal to 0 and I minus is equal to 0, and we substitute those back into the equation, and we see that the equation simplifies quite a bit so that we get that our output voltage V naught as a function of t is equal to or proportional to the derivative of the input voltage times the RC constant values. So this is how we get the name for this particular circuit. We have that the output behavior is dependent upon the derivative of the input behavior. With regard to the integrator circuit, we are again going to use the KCL analysis technique at node V minus. This time we find that when we apply the KCL properties at V minus and then apply our ideal op-amp rules that V minus is equal to 0 and I minus is equal to 0, that our output voltage V naught is equal to or proportional to the relationship of the integral over the input voltage. And that's how the integral or integrator name has been applied to this particular circuit. So those are two circuits that they're used quite frequently in industry, and you can see now how the names were derived. It's definitely related to the mathematics of how the currents and the voltages behave. All right, one final application that we'll look at from a capacitive perspective is for all of you who are music fans, RC filters are an extremely important way to clean up the music signal and to decide what passes through each of the channels. So if you have a low pass filter, and they'll be called either high pass or low pass or other descriptions for these filters. But in a low pass filter, the low signals are passed through, but it blocks the high signals, the high frequency signals. And that's the intention of a low pass filter. Now these circuits are not DC. They do have frequency-based voltage inputs, and we will be studying some of those as we get into our AC chapters. But I thought I would show you this application for the music filter. So let's take a look at that. So in conclusion, we've actually covered a wide range of basic properties for capacitors and inductors. We've covered the current, voltage, and energy characteristics. It's this energy storage characteristic that will be really important as we move forward into our DC transient circuits. And we also followed through our analysis on the series and parallel behavior for both. And then we looked at a couple of applications for capacitors in op-amp circuits, leveraging some of the techniques that we've used in the past for analyzing op-amps, and that was KCL. That's it. Thank you.